Hi, I'm Gary, and thanks for checking out this video. Today we're diving into a classic DSA interview problem in Swift and giving it a proper Swifty treatment. These kinds of problems show up all the time in tech interviews, so they're a great way to explore some of Swift's more advanced features. Even if you already know the algorithms, you might learn something new about the Swift language and the power of the standard library. In this episode, we're building and then reversing a linked list. Linked lists are a pretty old school data structure. I first met them at university, and that was ages ago. Plenty of developers will tell you that they rarely use them in real projects. So why bother looking into them? Well, mainly because they still pop up in interviews, and working with them gives us a great excuse to dig into deeper Swift's concepts, especially value semantics. This is the first video in a short series on linked lists, and it sets the foundation for what's coming next. I'm assuming you already know what a linked list is, so we'll get straight into the Swift side of things. I'll be demoing everything inside an Xcode playground with some starter code ready to go. So let's jump in. So here we are with the code pasted into the playground, and as you can see, it seems to be working. We've got what certainly looks like a linked list down here at the bottom and one underneath it that's been reversed. So let's just take a look through what we've got. Well, there's a definition here for a class. That's interesting. I wonder why we're not using a struct. We'll come back to that. The type is called list node. Okay, it's storing a value of type int. Well, straight away I can see that that would be better if it was generic. We just need a generic type in there, surely. Why would we just want to store an integer? And we've got a reference to the next list node. Maybe I prefer to call that next node, but okay, we'll leave that for the time being. We've got an initializer into which we pass the value. Yeah, again, we've got an unlabeled argument. I think that might be all right for value. And then we can also pass in a reference to the next node, which if we don't pass it in will default to being nil. Okay, right, well, so far okay. We've got a sort of general function for reversing the list. Into that we're going to pass in one of these list nodes, which can be optional, which is kind of weird. Why would you want to reverse something on nil? And it will return a list node, which can also be optional. Not really very keen on that as an idea. Oh, we'll have a look at it later when we perhaps go through the algorithm. We've got a print node function, so again we pass in a node. This time not optional. Well, that's good. And okay, well, that's obviously what's printing this output. We can look at that in detail. Oh, interesting that it's using print node here. So we've got some recursion going on. Interesting thing with recursion is that it is, well, it can make the code look very elegant, but we should also be aware that recursion does have a memory issue. If you're being asked to present a DSA solution and you shouldn't be using any more memory, well, other than something that's required obviously to run the code, then anything with recursion is probably going to be adding additional memory requirements onto the stack. So kind of something to bear in mind, that recursion might not necessarily be what you want. But anyway, that's working. So yeah, okay, so down here we're creating a list node with a value of 1, and its node is going to be this list node here with a value of 2, and it's passing in this list node, which is obviously doesn't have another node. That's the end. Fine. The head is obviously the list node, and we're printing it using this function, and then we're just reversing it. Okay, so that's then giving us a new head, and we print that out. Okay, that all seems fine. I think the first thing we're going to do is let's make this generic, because that just seems obvious. Let's actually no. The first thing we're going to do is I'm going to ask, why are we using a class here? Why can't we just have that as a struct? No, that's why. value type list node cannot have a stored property that recursively contains it. So you can't have a struct which in essence has got a reference to itself. Now, I have looked into this, and it turns out the reasons are quite complex, and I'm not going to go into them now, but if you want to have a look at the reasoning behind this, there are some quite complex arguments. So for the time being, we will just change this back to a class, but we ought to note something here now that we're in 2025, we've got Swift 6 and strict concurrency, and classes, particularly having mutable variables in classes, will cause concurrency warnings or possibly even errors. Now, we haven't got any here, so I'm not going to quite worry about it at the moment, but we should just bear in mind that this now is something that in a full project may need to be dealt with. Let's go ahead then and make this generic. We'll need to declare our generic type here as part of the class, and in here this will now be value. We'll need to do the same with the initializer, and we're also going to find that these functions, actually both the reverse list and the print, are going to have to be declared as having generic values. We'll put that in on this list node here. We'll have to return a list node of type value as well. Same down here with the print node then. We'll declare that as having a generic type. Are we done? Yes, we are. Okay, well, we're still compiling and working. We're not now just dealing with ints, we're dealing with potentially any type. I do have a code snippet here. Let's put that in and see, are we now able to create list nodes with strings? Yes, we are. And you can see that when we print it out, we've now got down in the console another linked list, but this time using strings rather than integers. And of course, potentially we could put any type in there that we wish, so we could have a linked list with really quite complex items. So I've just noticed that on the print node function here, we've got an exclamation mark. We are force unwrapping the reversed head. Now, force unwrapping anything is always potentially dangerous if you're not checking whether or not you've got an optional. Don't just force unwrap an optional. That can lead to a crash. But I'm not going to worry about that right now, because I have a feeling we're going to be changing this reverse list function and also the print node, because both of these functions, although we're passing in these list nodes, conceptually they're actually working on the whole of the linked list. Seems to me that actually what we want to be doing is creating a new type, and I'm going to make that a struct and call it a linked list. But of course it needs to support generics, so we'll give that the type value, and I think it only needs a single var. We'll call that head, and that will have a list node of type value, and it's offering to complete it for me, and it's making it optional. Well, that's a good question. Is there any point in a linked list that doesn't have a head? Well, I suppose if you wanted to create an empty linked list and you could later append nodes to it, then yes, I mean, we can have empty collections. So I think we will leave that optional. So now what I really want to do is move this reverse list function into my linked list. So what I'm going to be doing is reversing the list. Well, straight away I can see that I don't need this value parameter in here anymore, because it can infer that from the linked list type. Also, I think it's better if we just call this function reverse. Now, if you remember from before, we said that we would use the imperative of the verb when we're mutating the instance on which we call it, which in this case we are. We're not actually going to be returning a new list. So it's correct that we should use reverse, and well, we know what head is. We don't need this parameter anymore, so we can get rid of that. And actually, it's finding the head from the instance variable anyway, and we don't really need to be returning a function either. So the only thing we've got down here is we're returning the previous, but actually what we now want to do is set that to self. So, but it's telling me that self is immutable, and that's because I need to mark this function as being mutating. Okay, so that's compiling, but down here where we've got our test code, well, we're not working anymore. So what we need to do here is create a list. So because we're going to be mutating it, I'm going to put var list equals linked list, and we'll pass in the head, which is that, and we're still printing the head node, but of course we're not now reversing it on there. We're going to call the list, and we'll just call reverse on it. And what we need to call on here now, we don't have a reversed head. Instead, we're going to call on list that node. And but it's telling me we need to force unwrap that. Well, I think we're going to come back and get this right, but just for the time being, yeah, okay, I'll force unwrap it. And we're still working. Okay, we can see down the bottom our linked list is going 1, 2, 3, and here it is when it's been reversed. Okay, I'm happy with that. What about this print node function? Well, actually, what we really want to do is we want to be able to print the list. And a better way of doing that would be if, say, down here, we could just say, well, print the list. A way to do that is to make the linked list conform to a protocol called custom string convertible. And I've already written a code snippet for that, which we have here. Let's take a look. So we're going to extend linked list to conform to custom string convertible, and the only thing that protocol requires is a dynamic variable called description that returns a string. At the top we'll have a guard statement, and we're going to check whether or not the head is optional or not, and if there's no head or it's not defined, we'll just return an empty string. So now we've got a routine where we're going to start by initializing a string with the value of the head node, and then with a loop that's not dissimilar to the reverse function, we'll create a current node variable and set that to next, and while that node is not nil, we'll just append that to the result string. We'll set the current node to the next node, and we'll return the result. So what this means is down here, instead of now saying print node, I can just say print the list. And we can do the same with the reversed after the list has been reversed, and now we don't have any of those horrible forced unwrapping going on the optional. And just finally here, well, we haven't got a linked list on that, so we need to print, and we could just create a linked list. Whoops, what is it doing? Linked list with the head, with the string head, and that should output for us, yeah, what we had before. So that's looking a lot more elegant, and this print node function, well, we just don't need that, so we'll get rid of it. So just for a bit of fun, I thought perhaps we could also make the list node conform to custom string convertible. So we'll put in here another extension on the list node, and we'll get that to conform to custom string convertible. And no doubt Xcode is going to now tell me that it doesn't conform to the protocol, so I'm just going to add the stubs for conformance, and you can see it's just a single dynamic variable of description which is going to return a string, and all I'm going to put in here is the value. So you'll wrap that up in a string, and that's all we need. And now if we were to ask for a node to be printed, it's just going to print the value of the node. In fact, we can try this down here. Let's just print the head now. That should just give us the number 1. Yeah, it does. We can see that down here in the console. So I'll get rid of that, but it means that in this extension on the linked list for custom string convertible, we don't actually have to call the value anymore on the node. We can just ask for a string description on the node itself, and we get the value, which is just a little nicety. Okay, so the next thing I want to look at is the idea of getting the linked list to conform to a Swift protocol which is sequence. It seems like it's an ideal candidate to conform to sequence, and that means that we could enumerate through the nodes in a linked list using a for-in loop. So let's add another extension onto the linked list, and we're going to get it to conform to sequence. Now it's telling me that it doesn't conform to sequence, and in order for the linked list to conform to sequence, I need to declare a function in here which will return an iterator. Okay, now what exactly is an iterator? Well, that's something that conforms to the iterator protocol. Now, to save me typing it all in, I'm going to complete it with this code snippet where I've defined a struct for a linked list iterator which conforms to the iterator protocol. It declares in it a private variable which is just basically the current node, which means that the iterator is able to keep a track of, well, which node it's currently looking at. I've declared another initializer where, well, just to make it look a little bit nicer, we're going to pass in the head of the list, but that just then gets set onto the current node. The iterator also has to declare this function next, in which it's going to return the element value that we're iterating through. And in this case, it's going to be a list node, which is obviously typed to value. We notice that it's optional, because if we ever return nil, that's the way of signaling that we've finished iterating through the list, or the sequence, I suppose. Here I've got a defer statement. This is really handy. It saves me having to create, in effect, a temporary variable to set the current node on a node, and then I can increment the current node before I then return that node as a temporary variable. Well, what I want to do here is I want to increment current node, but obviously I actually want to return it. So that defer statement will not get executed until after the function's effectively returned. So the only thing that we now need to do is just complete this make iterator function here, and what we're going to be returning is a linked list iterator, and we just need to declare it in here or create it, and we'll pass into it the head of the linked list, and that's all we need to do. So now we should find that the linked list conforms to sequence, and we can test that down here by saying for a node in, well, we have that list defined, and we're just going to simply print the node. We should find at the bottom in the console we get the numbers now. Yep, 3, 2, 1, because the list had been reversed, and that's now iterating through the list, and that's actually really quite neat. In fact, we could probably use that in some of the functions that we have up here. So let's say, take for example the reverse function, where we've got this current for the head. Well, in this while loop, we probably don't need this anymore. We could just simply say for node in self, and well, we'll let the next node equal node.next. Oh, we need to put a curly brace in there. We don't need this current anymore, and yeah, we don't need to do that. Is that now still working? Yeah, it looks like it is. So that's kind of quite neat. It's a slightly neater idea. We don't have to keep declaring all these variables or this current node. So we could probably do the same here. I think we might have to rework this function a little bit. Let's change this for a for node, let's say in self. Now this result string, we'll keep the guard. That seems right. We don't want to start with a string having any value in it, I don't think. We don't need this current node, and it can go out of there. And I think what we need to do is say, yeah, each time through, if the result is empty. Actually, I think it's when the result is not empty. If the result's not empty, then we need to say result plus equals, and that's where we're going to put the little arrow in. Otherwise, the result will just be plus equal to the node. I think that's right. Oh yeah, look, that's working if you look at the console at the bottom. So a slightly different approach, but we are now using that sequence. So just to recap on what we've done, we started off looking at the list node. We've made it generic, which is always a good thing, so we can have a linked list of any types, and then we kind of wrap that up in a linked list type. So any of the reverse function now, that's going to act on the whole of the list. We've used some Swift extensions on this protocol for custom string convertible. That means it makes it nice and easy for us to just print both the nodes and the list. And then we also added an extension on the linked list so that it conforms to sequence. Now, one of the things that we could also get a linked list to conform to is collection, but that's a little bit more involved, so we're not going to do that on this episode, but it is something that we'll look at for the next episode. And I think that kind of wraps it up for today, except there is just one more thing. One of the features of the Swift language is that it allows us to create our own custom operators. These can be either prefix, postfix, or infix operators. I have a code snippet which I'm going to insert here. In this, we're creating our own infix operator, specifically this arrow. It's called an infix operator because it operates on two operands, those on the left and the right of the operator. We can't use the arrow we've been using when printing the list, because that symbol is already part of Swift's function syntax for specifying a return type. If I try to define it, the compiler gives an error. So instead, we're using two dashes followed by the right angle bracket. To start with, I'm defining a custom precedence group called list node precedence. I'm not going to go too deep into precedence groups here. You can read more about them in the Swift documentation. But the important thing is that I've set the associativity to right. We'll see why that matters shortly when we look at how Swift expands expressions when parentheses are not explicitly written. Right associativity tells Swift to evaluate the expression from right to left. Next, we'll define the actual infix operator and tell Swift that it belongs to our new precedence group. After that, we implement a function for the operator. It's similar to the way you'd write a custom double equals when conforming to equatable, or a comparison operator when conforming to comparable. The operator takes a left-hand side and a right-hand side, both of which are generic list node instances, and it returns a list node. All the function does is set the left-hand side's node next pointer to the right-hand side node, and then return the left-hand side so we can continue chaining nodes. I want to give a quick shout out to Dave DeLong, who wrote a great blog post about building an HTTP package. In it, he uses the idea of chaining loaders together with a custom infix operator. That's where I first saw this technique. I'll leave a link in the description if you're interested in his approach to HTTP loading. One quick word of caution. Just because Swift lets you create your own operators doesn't always mean you should. The last thing we want is Swift code that starts looking like regular expressions. But in this specific case, I think defining a custom operator gives us a much cleaner, more expressive way to chain nodes together in a linked list. Let's look at how this works. In the reverse function, I notice that we can now delete another line that's no longer required since we implemented the for in loop. Also, we're setting node.next equal to previous, but now we can simply chain the nodes together using our new operator. It's now clearer exactly what the intent is when we are linking nodes, and as we can see, the result compiles and behaves in exactly the same way. Scrolling further down, you can see that originally we built the linked list by nesting initializers. We start with a list node of 3, which gets passed into list node of 2, and this gets passed into list node of 1. That's why the operator's associativity is set to right. We want Swift to evaluate the expression in the same order as those nested initializers. With this new syntax, we can rewrite this structure using the link operator. And in doing so, we make the code more expressive and easier to read. As you can see, everything still compiles, and the list is constructed exactly as expected. In fact, so much so that let's just add another node to the end of the list and see this extended list in the console. So that's it for this episode, but there is something else I want to check before we finish. First of all, I'm going to make a copy of the list and call it list2. Then, just to be clear, when I print the lists, I'm going to give them a label so that we know which list we are printing. And we'll do the same with list 2. Let's just check what we have in the console. Okay, list and list 2, which are both the same, and this is what we expect. We then reverse the first list, and I want to print both lists again. In this instance, we should see that list 2 remains unchanged because that's how copy semantics works with value types, and the linked list structure is a value type. But this isn't what we're seeing. The first list and list 2 start by being the same. We then reverse list, which is reversed and printing correctly. But list 2 is now, well, it's messed up. It's only got the first node. List 2 should not have changed. This is how value semantics works. Something's gone wrong, and I'm going to leave you to think about what that is. And that's it for this episode. I hope you found it interesting and maybe picked up something new about Swift along the way. I'd love to hear your thoughts. How do you feel about creating custom operators? And what do you think is going on with the linked list not copying properly? Drop your ideas in the comments below. If you want to see more videos like this, don't forget to like the video, subscribe to the channel and turn on notifications so you don't miss the next episode. Thank you so much for watching, and I hope you have a great day.
you.